My name is Tiniyam Ganesh, and I'll be doing this third part of machine learning, data science, NLP, and big data. So in this, I will be covering Apache Edgent. Then I'll be touching on some aspects of natural language processing (NLP), and finally I'll be taking a look at big data with Apache Spark. I'll be closing this discussion with some of the dangers in data science, and so that will be this will be the last and final session of this big data, data science, NLP, and machine learning. So let's get started. So data science impact. Data science has had an enormous impact on almost all the fields that you can think of, whether it's mobile, social, Internet of Things, cloud computing. Besides, we also have, you can take the impact of data science and analytics in finance, retail, manufacturing, etc. So there's an enormous impact all over, and it is extremely critical in today's world, particularly with the aspect of explosion of data. So as I just discussed, it is impacted, has significant impact in several areas. So now I would like to talk about another interesting area, which is analytics at the edge, also known as Apache Edgent. So this was previously known as Apache Quarks, and Apache Edgent is essentially analytics that you perform on sensors which are there on the edge of the network. So in typical machine-to-machine communication, we have these sensors which measure various parameters from the environment and then send data to the backend for processing. Now, in this context, we have these millions of sensors and actuators on the edge of the network, and typically we don't want too much data to come into the backend and bombard our backend server. So this Apache Edgent, what it does is, it's a model that is embedded in gateways at the edge of the network, and this Apache Edgent can run analytics at the edge of the network, primarily for the Internet of Things, and it's a runtime and a programmable module that works on streaming data. So it's a microkernel type runtime that can be embedded in gateways and small devices, and it performs analytics at the edges, and you can use it on a lot of on vehicles and systems and appliances in manufacturing, etc. And the nice part about this Apache Edgent is that it doesn't try to send all of the data. So it only sends interesting data from the sensors to the network. So if 99% of the readings were normal and there were just 1% anomalies, then it would just transmit those anomalies to the backend server for further processing. So it takes intelligent decisions, and it sends the data back over the network. So for example, it could check for a maximum in a window of time, or it could compute the average and just send the average in a specified window which you are trying to measure as it receives a stream of data. So it just essentially sends a small amount of data in periodic, not periodic, as in when the particular criteria is met. So the backend server can take appropriate action based on the measured values. So for example, you can have a connected devices, connected vehicles with Edgent, and you can have Edgent actually adjust the traction control based on the weight of the cargo and all the passengers. So also, for example, in a truck, in a fleet of trucks, you can, based on the data received from the sensors, you can adjust the roads and the loads that, based on the loads, the amount of load the truck would have to carry. So now let us look at another interesting area, that is natural language processing. NLP is, has taken a lot of center stage in the last several years, starting from 2008 when deep learning has entered into our mainstream. So I mean, we have a lot of natural language processing is there embedded into our lives. So we have Siri from Apple, we have Cortana from Microsoft, or IBM's Watson. All are capable of this natural language processing, receiving input in regular English and also responding. But NLP actually encompasses several areas including computer science, artificial intelligence, computational linguistics, etc. And if you look at the domains, it spans a whole lot of domains from linguistics, psychology, information theory, mathematics, and statistics. But it is pretty difficult to do natural language processing, and this is pretty obvious because of the inherent ambiguity that you have in the English language. So for example, if you take two sentences, time flies like an arrow and fruit flies like a banana. So in the first sentence, flies is actually a verb, whereas in the second, fruit flies is actually a noun. So even though the sentences look alike, there is an inherent ambiguity, and that is where the difficulty of doing NLP becomes very significant. And there have been two main approaches to NLP. The first is the rationalist approach, and the second is the empiricist approach. The rationalist school was led by Noam Chomsky, the famous linguist, who strongly believed that there was a structure to a sentence, that you need to look at the sentence structure before trying to do any analysis of the sentence. And he gave an example of why the problems can rise. So he gave two sentences: colorless green ideas sleep furiously, and the second, furiously sleep ideas green colorless. So even though both sentences are actually meaningless, you can make out that the first sentence actually seems to be more sensible, seems grammatical, but the second sentence just seems to be a jumble of words. And he said that this essential knowledge of the grammatical rules is pretty important in doing NLP. But in the 1980s, with the amazing improvements in computing and computing power and the drop in the storage prices, the empiricists who believed that NLP can be done purely on statistical analysis made significant improvements. And they came up with probabilistic language models for doing natural language processing, and they used machine learning algorithms for this. So NLP is based on what we call as an n-gram model. That is, you take a large corpus of text. So it could be tweets, it could be Facebook updates, it could be news articles, it could be blogs. You take all the text, could be Wikipedia, and you create n-gram model. So for example, a 1-gram model would be a representation of all unique single words and the counts of those words. That is important. Or you could take a bigram model in which you take all representative of all combination of two words and the counts found in the corpus. So for example, going to, or the shop, or the market, something like that. You take all those combinations and you take the counts. And similarly, we can have trigrams where you take a combination of three words from the corpus. Corpus is essentially the text that you are providing for the machine learning to happen. Or you can take a quadgram or n-gram. Typically, you don't go beyond a quadgram, that is a combination of four words. For example, the probability of the sentence, the quick brown fox jumped, you can say the phrase, is equal to the probability of the word the, and then into the probability of the word quick following the, and into the probability of brown following the quick, and so on. So that is how it is actually calculated. And then we have something known as the maximum likelihood estimate. So what is the maximum likelihood estimate? Marco came up with what is known as the chain rule, that he says the probability of word, given that a word has already occurred, is known as the maximum likelihood estimate. And the way we compute that is the probability of a word wi, given that a word occurred before that, that is wi minus 1, is equal to the count of the word of the two letter the combination of two words wi minus 1 followed by wi divided by the count of wi minus 1. Similarly, the maximum likelihood estimate of a trigram is the word wi, assuming that you already have the words wi minus 1 before wi minus 2, which is equal to the count of the combination of these three words wi minus 2 followed by wi minus 1 followed by wi divided by the count of wi minus 2 divided by count of wi minus 1. So there are different techniques for doing this NLP based on the maximum likelihood estimate. One of that is known as the Laplace smoothing. So what will happen is, if you take, for example, the combination of two-word combination, that is the bigrams or diagrams, you will find that there are certain combinations which have a probability of 0. So for example, you could have some estimate for the market, or but you may not have any counts for the combination market the. So what Laplace smoothing does is, it tries to but that does not mean that the combination market the may not appear in your future when you're trying to predict the text. So what this algorithm does, it tries to add a 1 to all two-word combinations which have the maximum likelihood estimate as 0, and since you're adding a 1 to all that for non-existent bigrams, you will have to subtract that appropriate amount from the bigrams that already exist. The reason we do that is, we know that the sum of the probabilities over your probability space has to be equal to 1, so you will have to subtract that. So the way that is done is, this Laplace smoothing is done is, the probability of a word given a word occurred before wi minus 1 is equal to the count of wi minus 1 wi plus 1 divided by the count of wi minus 1 plus plus v, where v is where you add this for every one you add it for all the words that occur before it. And then we have a back off algorithm, where if the phrase is not found in the n-gram model, then we need to back off to the n minus 1 gram model. That is, if you don't find a particular combination of a three-word combination, you can, that is a trigram, you back off to a bigram. Deep learning has been used in natural language processing, and it was trained on 600 million examples, and the learned features, most interestingly, was also able to capture semantic distinctions just by looking at a string of the words. And this is where the most amazing thing occurs. While we would assume that you would need to know the sentence structure as enunciated by the rational school of thought, we find that when we use these advanced machine learning techniques like deep learning and neural networks, the network is actually even able to infer the semantic structure of the sentence. So for example, if I give you a sentence like, she scrummed him with the frying pan, what does the word scrummed mean? Incidentally, this example is taken from the Coursera course, Neural Networks for Machine Learning by Professor Jeffrey Hinton. And so anyway, from by looking at the sentence, you can guess that the word scrum means probably hit, or tapped him with the frying pan, etc. Okay, and so essentially what I'm trying to say is that as a human, we can infer, even though we may not have come across the word, we can infer the meaning of the word, what it's trying to say. And this chart shows a 2D map of 2005 commonly used word, and deep learning was performed on a rich corpus of text. And you see, interestingly, this deep learning network has been able to club certain groups of words So you can see that a cup, medal, prize fall into one kind of a category, and then a player, a winner, and a team fall into another category. And so essentially what I'm trying to tell you is that with the use of deep learning networks with multiple hundreds of hidden layers, etc., and using recurrent neural networks or convolutional neural networks, deep learning networks, the network can actually infer the sentence structure. Here's an even bigger example of where the deep learning has been able to find a sort of a pattern in the sentence structure from the corpus. So I will show you a demo of some NLP applications that have developed. And in this application, I've ingested the entire corpus of Shakespearean works, and then I tried to predict what would be the next word that Shakespeare would say. So now I will finally get into big data, and I particularly big data with Apache Spark. So where does big data come? As I said, we have already seen that data that it is exploding, and there's an exponential increase of data from machine to machine devices, from smart grids, and also generally from, so big data come from web clicks. These billions of users using the web, they are clicking different pages. You have ad impressions, server requests, multiple servers all over the internet, transaction, updating posts, billions of Facebook updates, tweets, Instagram photos, etc. So here in this chart we see the data. So Large Hadron Collider per year, the number of the data it generates is about I think 25 petabytes, and then tweets per year, human memory, etc. And here even social networks, road networks, telecom networks are also examples of big data. And there are three main features of big data. Typically you have data, the volume, velocity, and variety. Volume, it's growing at an exponential rate. Velocity, the rate at which the data is being generated, is tremendous. So there's an enormous velocity in the data. And finally the variety. So you get all sorts of data, whether it's structured, unstructured, CSV, XML, JSON. So these are the three B's of big data. And typically, if I had to sum up big data in a single word, big data is when we can't get all the data into the memory of a single computer, and we have to use multiple servers. So that's where big data actually arises from. So what and why of big data? Data is going faster than the computation speeds and proliferating data sources. Storage is getting cheaper but limited by the CPU speeds. So for example, Facebook daily logs about 60 terabytes, 1000 Genomes project is 200 terabytes. The Google Web Index, that is, it crawls the web and it creates a web index about 10 plus petabytes, etc. So the big data problem is one machine cannot process or even store all the data, and the solution is to really distribute the data over multiple servers and machines. And in this chart, I show you the speeds of data transfer across devices. So you can see from the CPU to the random access memory, it's about 600 megabits per second. From a CPU to the switch, it's about 10 gigabits. The nodes on another rack, it's about 0.1 gigabits per second. And this session will be about Apache Spark. And Apache Spark actually came much after the MapReduce algorithm, which Google came out with. And in a typical MapReduce, you would find that we perform a map operation on a distributed data set, and then we reduce the mapped data and get the final output. But you can see that there is a lot of disk I/O that is happening in MapReduce. So MapReduce, even though it is an extremely efficient and a good solution when we for big data, but it also involves very heavy disk I/O. For every map we have to get the data, then shuffling, we'll probably again send to data and read from data, and then the reduce, you'll compute it and again write to data. So there's very heavy disk I/O. But incidentally, processing powers have increased enormously, while the memory cost of memory has dropped significantly. So you can see the drop in the memory prices over the years. It has almost come to 1 cent per megabit for a flash memory. So what is the approach? Is that we try to rather than doing all the computations in the disk, we can do a lot of computations in memory, and that will result in a significant improvement in the computational power. And this is what Apache Spark does. So you can see the differences between Apache and Hadoop, Spark and Hadoop. Hadoop is disk only, whereas Spark it is in memory, or it could be on disk. Hadoop uses the MapReduce algorithm, whereas Apache Spark has many transformations and actions. And Hadoop typically uses Java, and Apache Spark uses Scala, Java, R, and Python. This is a Spark timeline. 2004, Google came up with the MapReduce paper. In 2006, Google picked up this MapReduce, and then they came up with this Apache Hadoop, which became very popular. They came up with a lot of languages like Pig, Highway, etc. And 2010, there was a Spark paper from the University of California, Berkeley. And so there's been a lot of interest in Apache Spark because of the phenomenal increases in computation speeds over MapReduce. And how does Spark work? You have the driver program in which you create a Spark context, and then you have a cluster manager which gives the small tasks to these worker nodes. So each of these nodes perform some individual tasks, and they take input from Amazon S3, HDFS, or other storage. So Spark computing uses what is known as resilient distributed data sets. You write programs in terms of operations on distributed data, and it is also fault tolerant. What does Spark do when a worker crashes, or if a particular worker in which a task power is very slow? Spark just kills that worker and starts a new worker. And Spark works on data frames, so it could read files from the HDFS or parallelizing Python collections, etc. So Spark has essentially two main operations. One is known as the transformations, and the second is known as the action. Transformations are lazy, that is, they are not computed immediately. You can perform a set of transformations. I'll come to what transformations mean. And then when you perform an action, that is when the computation is actually done. So transformations are filter, sort, order by, distinct, group by, etc. Actions are show, collect, take, and count. So for example, if you have a set of distributed data, then you can try to map. You can, for example, you want to do a square of all the data. You can just say map, and you can square all the data, and that will perform that operation on all the data. But as I said, or you can do filter. You can give a particular criteria and then apply that filter across all the data in your across the several server clusters. But as I said, transformations are not applied immediately. They are they are done lazily. And then when you do a reduce, that is when the actual computation will actually happen, or a collect, that it will collect all the results that happened for your filter or any of the transformations. What happens is, when you do the transformations, the set of transformations are not computed, but they are created as directed acyclic graphs, DAGs, and then the action actually optimizes these acyclic graphs and then takes the appropriate action, so that the processing is very efficient. Okay, so here again we are seeing the same thing. You have a driver program, and it then runs these tasks in separate workers. And also some of the other techniques that Spark does is, it does something known as, since machine learning, typically you have to use these large matrices, multiply matrices, whether you're doing linear regression or logistic regression on neural networks with gradient descent, you typically have to do huge matrix manipulation and multiplication, etc. And Spark uses distributed computing, so it uses a technique known as outer product, and so which is particularly efficient when using the MapReduce operation. And Spark has multiple modules: the SQL module, the streaming module, machine learning library module and a graph module. And many applications big data is used real-time targeting. A retailer can target by analyzing all the behavior of the individuals while shopping. It can update preferences and try to model their behavior and target. Similarly, you can have manufacturers in production line analyze the sensor data and regulate the process to cut waste. But here now we come to an important aspect that correlation is not causation. So one of the we have seen a lot of things. You've seen machine learning, data science, and NLP and all that. So what is correlation is not causation? This is so. For example, here are two fun charts. The first chart shows both these charts show spurious correlations. So the first chart shows the suicides, the US spending on science, space and technology, and the suicides by hanging and strangulation. It appears that the US spending, which is in red, and the hanging and suicides follow each other pretty closely. But or if you take the second example, you find the number of films Nicolas Cage appearance, this is the black line, and the number of people who drowned in a pool seem to follow each other pretty closely. So it looks like there is some correlation, right? But clearly these are two nonsensical examples, and though the two lines seem to follow each other, does not mean that they are actually correlated. And there's a very interesting example incident which happened in the last couple of years, that Princeton they came up with a paper known as the epidemiological modeling of online social network dynamics, in which they claim they do some analysis by searching the Google Trends, and they claim that the best fit model in the future predicts a rapid decline in Facebook activity in the next few years. And how they came to this conclusion was they looked at the Google Trends searches for MySpace. Google Trends, you can go and check out the trends of different things. You can just type in a keyword, it'll tell you the trend. So MySpace, it went to a peak and then it declined. And they said that Facebook also in the year 2012 has reached a peak, and the number of searches in Google Trends is dropping. So hence Facebook will disappear in the next couple of years. And Facebook came up with a very sarcastic response, in which they came up with what seemed like a research paper, and they said, keeping with the scientific principle that correlation equals causation, they say that our research is unequivocally demonstrated that Princeton may be in danger of disappearing entirely. And the way they do it in a similar method, they look at Google Trends and try to find the number of searches for Princeton, and so based on the Princeton search trend, they show a declining trend, and they say this trend that suggests that Princeton will have only half of its current students by 2018, and by 2021 it will have no students at all. So this was basically a sarcastic response to Princeton University's research paper. But the key thing I want to just highlight here is that we should be careful not to take a correlation as causation. Okay.